All right, we're just going to pick up right where we left off in the last video. Now, if you were working on the Knowledge Review Challenge and found yourself stuck, I hope that the last video provided the inspiration required to get you unstuck. Now, if you're still stuck, that's okay. You can follow along in this video as we continue pushing our way through to the completion of our hierarchical graph application. So at this point, what we'd like to do is go ahead and begin focusing on only the transform node. We'll get back to shape nodes and all the other stuff that we can do just a little bit later on. But we need to start off with the transform node and with the requirements. Now, why did I pick the transform node as our starting place? Well, simple. As we said in the last video, the transform node, that kind of lies at the whole heart of the hierarchical idea. I mean, if you take a look at the drawing that we have on the board right now, the left-hand side demonstrates what we're trying to achieve, a hierarchy of transform nodes. And so inside the transform node class is where we're going to find the meat of the application, if you will. So let's go ahead and start out with the requirements for the transform node. So I'm going to leave all of the gibberish that I've written all over this board up and available just in case I need to refer back to any of the things that I drew in the last video, because all of this stuff will probably become important at one point or another. So we'll begin by creating a new whiteboard. All right, so we're going to be looking at requirements. So the requirements of the transform node. Well, first of all, we know that we are going to need to maintain a reference to a shape node, right?
That's right, because I mean we need to use a shape node for any type of rendering, and it would be useful to have all of the transform nodes able to do that lookup.
Exactly.
So that if we're ever looking through all transform nodes, or if we just want to view everything as nodes, non-specific nodes, because everything depends from node, then we'll be able to retrieve those.
So what if we had like a private shape node, and we just call it, say, shape.
And then that, just like on the whiteboard you drawn in the previous video, that would give us our link from any given transform node over to its relevant shape node, providing it had one.
Exactly. As a matter of fact, see, here I am already wanting to demonstrate that. So what we just created is this right here, that particular field. And that's where we'll store that reference pointing over to a shape node. Okay? So let's go ahead and jump back in here. Let's see, what else would be handy? Now, we could take this out, because, again, we're in the design phase right now, so we can always alter this if need be. But just thinking about it, it would be nice if we were able to gain access to our parent transform node without having to start looking at all of our lists. I mean, if we look back over here, once again, pardon me for jumping around, but like I said, I felt this would become very handy. If I wanted to, as a matter of fact, I want to draw on this one too, so let's make sure that we have focus down here. If I wanted to take a look at Transform 2 and tell you who the parent was, how would I go about doing that? Because so far, everything that we've done has required walking down the hierarchy. We haven't really looked at what's required and looking back up it. So in this particular case, what would we need to do? Well, we would need to more or less start off at a root level, work our way down towards ourselves, and always remember who the last guy was before we walk down.
Or another scenario you might find yourself in, as we demonstrated what would be necessary in this scenario to take the ball from being at the root level and moving it into the hierarchy. We showed taking it out of the root list and putting it into one of the child lists of a transform node. What if you had a different scenario? What if you were simply moving it inside of the hierarchy, taking it out of the list of one transform node and putting it into the list of another? The list that you're taking it out of is its parents'
children list.
If you don't have access to its parent, you can't find that, and you wouldn't be able to properly remove it from a certain branch in the hierarchy.
Ooh, that's a great demonstration. So it would be nice to, and let me just add this in with some color. How about we do this with some sort of nice blue? So what if we were to keep or add, so all of these guys now get a parent field, and with the parent field, Now remember, these are still inside this instantiation of the transform node class, okay? Just drawing it with a new color to show you that here we are doing just a redesign on the fly, just adding features to this. But it works well because we're able to use the design that we started with and we're just building on it now. So here in this particular case, we know that ball is as a matter of fact, I can come in here and clear this out just a little bit. That looks nice. We know that transform 2 is a child of the transform 1 transform node. So we can come in here and say, all right, who's the parent going to be? Well, the parent's going to be TXFRM1. So now we have just pointed back up to our parent, which, as Logan just said, is very convenient, where if I was to take transform 2 and unparent it from this guy, I would need to make sure that I removed him from the parent's child list. So here you see him in the parent, which is transform 1, in his child list, as I just drew an arrow pointing to him. I would need to remove him out of there. Well, now, by maintaining a reference inside the instance of the class, inside this specific transform node, back to the parent, I can quickly gain access to that list, the list of children, back up in the parent. So I think that's a fantastic idea. So he would be pointing back up to there. Down here in box, box is currently, let's look up here at the diagram, box is at the moment a child, as seen right there, of transform 2. So with him, what we would need to do is, let's go ahead and pull this back down, is point up to transform 2. And so now I can quite quickly get up here to transform 2. So let's definitely do that. I think that's a fantastic idea. So let's come back over here, change our color back real quick. I just wanted a different color so you can see how we're going about adding on to our design. Now let's jump back up here. And scroll back up. All right, so let's keep track of that. So to keep track of that, how about we maintain a private, well, what is it that we're wanting to keep an eye on? Transform node. So a private transform node. And that is the type. What do we want to call it? How about parent? Make sense to you, Logan?
Yeah, it's the parent of this current node.
You got it. Now, inside of transform node, because remember, this is requirements for transform node class. We've already said that the class itself needs to maintain, the type object needs to maintain a static list of all the root nodes. So we're going to definitely need to make sure that we come in here with a private static list. What's the list going to contain? Transform node. Okay, and what do we want to call this list? As Logan suggested in the last video, root nodes. So there you go, it's a static list. So now we can simply say transform node dot root nodes. So it'll give us access straight into this static list that will contain all nodes that are at the root. All right, so what else? Well, we know with each instantiation of the transform node class, each object needs to maintain a list of children, as we demonstrated over there on the memory diagrams. So let's go ahead and create a private list. Notice how I am not using static. Why am I not using static? Because this needs to be created with each instance. So each object, each transform node needs to have its own list of children. So once again, it's a list of transform nodes, and we'll call this children. So what goes inside this list? Transform nodes. Simple enough. All right, very good. So Logan, I think that's enough for data members to get us started.
Right.
It
also satisfies all the requirements that we saw before. We have a shape node, and that was drawn out on the board before. We have the parent, which we just recently added. We have the static list that resides that holds root nodes, so we have that in place.
So a master list of all nodes that are at the root.
And then we have a list of children nodes or child nodes in each individual transform node that gets created.
Right.
So that should satisfy everything that
was
drawn.
So our children list is an instance data member. So it goes along.
Because we have a different one with each instance of each transform node.
You got it. And our root nodes, that's just one list. It belongs to the type object. All right, very nice. So now let's go ahead and take a look at what kind of methods are we going to need. Ooh, this is where the fun begins. What kind of functionality does root nodes need to have? Well, it's going to need a static constructor to fire off the creation of the root node static list. So let's just come up over here and static. Let me think how I want to draw all this out. Again, it won't hurt anything. I'll just go ahead and draw out the whole thing. So static transform node. And what's his job? It's going to be to create the root node list. All right, from there, I'm going to need some constructors. I'm going to need my regular instance constructors. I'm going to need transform node, but I'm going to give transform node, I'm going to give two different flavors of it. I'm going to give just a default constructor, so that anywhere along the ways I can create a transform node by just saying new transform node. But what if I'd like to be able to create a new transform node with a specific name in mind? Like I'm going to create a transform node called ball, as I demonstrated back over on the memory diagram. Well, it'd be nice to be able to say new transform node and then pass it the name that I want that transform node to be. So we're going to need two different constructors to take care of that. So we'll have a public constructor that's just transform node. Now I'll revisit its initializer in just a second. We also want a public transform node that is going to take in a string called something along the lines of name. Now, check this out. I'm going to add an initializer to my default constructor, so we'll put in colon and turn right around and call this. So it's going to call another constructor with the overload that takes in a single parameter of type string, meaning I'm going to call the transform node that takes in a name, and I'm going to just pass it transform. Now let's all think about this for just a second. With the way that this is set up, it looks as follows. If I say new transform node and don't pass anything, it's going to create me a transform node named transform, as indicated by this guy turning right around and calling this guy and passing transform into it to be used as its name. Well, that works great for the very first one we make. Now the second one we make, he's going to be called transform also. That's a problem. That means inside of here, we're going to end up needing some name validation. And guys, let me tell you what I'm doing right now. The way that this is all being presented at the moment is I'm telling you, this is how Logan and I sit down and design stuff. We're just talking. This is just a relax, let's talk about it. Not structured lecture at the moment. And so think about it. So we don't want two different transform nodes both named transform. So if we add some sort of name validation, meaning let's take in a name. Now I don't want to turn around and tell the person that just asked me to create a new node, or tell the other class that just asked me to create a new transform node, that we can't because the name is not valid. So in our name validation, how about we just try to append a number to the end of it? So if transform is no good, how about we assume that it's going to be the second transform node? So we try calling it transform 2. And if that's no good, we try calling it transform 3. If that's good, then that's the name of it. So let's put some sort of name validation in here that will not cut us off from creating a new transform node. It'll just simply look at appending a new number to the end, and it'll keep doing that until finally we have a unique name.
Right. We want to make sure that we never cut ourselves off from being able to create a unique name, because we have a default constructor that calls the other constructor with a parameter transform.
That's right.
Which would mean that it has to succeed somehow. Otherwise, the default constructor could come up with non-unique names.
Exactly.
Because with the default constructor, we don't have the option of saying, whoa, 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 don't make a node. We don't have that option. If we get to the default constructor, we are making a transform node.
That's right, because what's its job to do? To instantiate that class. And so we now have a transform node. Now, if we wanted to turn around and rethink our design and come up with a factory method, then we could go in there and say, let's see, is this name valid? Yes, it is. Now create a new transform node and return a reference back. We could do that.
Right, but that's an additional layer of code that has to be put in, because it's like a pre-creation handler to make sure that it's okay.
Exactly.
The other option is what we're going to put in place here, and that's where we validate the name by continuing to add numbers until it becomes unique.
Precisely. Okay, so we know that later on we're going to have to worry about name validation inside of our transform node public constructor of overload one parameter of type string. Okay, good. All right, so let's see. What else are we going to need? So now that we've got some constructors that will handle kicking off the instantiation of the transform node class for our object and handle naming, now let's turn around and do stuff like, how about a public set parent? Because now we're at a point where we have the transform node existing in the heap, and it has its own list of children, and a reference to its parent, and a reference to, you see what I'm getting at? It has all this stuff in it, but now we need some real functionality in place. So let's go ahead and simply say, set parent will allow us to come in here and tell it which transform node is going to be the parent. So transform node, and we'll simply pass in, it'll be held in parent. Good enough. I mean, the bottom line, the behavior, what's the behavior to do? It's to set the parent. Okay? So now what else can we do? All right. How about things like show all? Okay? So we could basically walk through and show all of the nodes out there. Does that make sense? All transform nodes.
Right off the bat, that's going to be very helpful when you're creating this architecture and you want to see if it is indeed working. We need something that will be able to go through and give us a list of all nodes that have been created so far. And it would also be helpful if that display would show the parenting, give some visual indication of how parenting is taking place. And we can use that to verify that our network is indeed working.
And we'll set this as static.
Because for a show all, that only makes sense. So we go all the way back to transform node and ask it to give us all of our transform nodes, much like we did in cases where we had a simple list of things, like, for example, a list of actors. We would throw that static list inside of actor itself. So if we ever wanted to ask for that, we'd ask it for it from actor.
Exactly. Now, what if we wanted to start showing stuff from a specific instance of the transform node? So let's say that we had created a hierarchy that had a shoulder joint, then an elbow joint, and from the elbow joint it went down to a wrist joint, which then broke out into its children being into the thumb and your fingers as a representation of a hierarchy real quick. How about if I said I wanted to see, starting at the elbow, show me all of its children? All right, so in that particular case, how about a show tree that it's not static? A show tree would actually be a show tree would actually go about.
It would actually be a method from a specific node.
From a specific instance. That's what I'm looking to say.
It would be called from a specific instance. So you could say, all right, from this given instance, show the tree from this instance on down. So that way, if you had started at the shoulder, if that was the node that you called this upon, so you tell the shoulder to show tree, what it should do is show all of the children, which would be things like elbow and hand and fingers. But it would not show things like collarbone, hips, knees, feet, and things like that, because those aren't part of its tree. They don't descend from it. So show tree is basically kind of like show branch or show descendants. That's its purpose. But we'll call it show tree, as in show the tree from the node that it is called upon.
And it will take in an integer that'll be a depth. Want to talk about the depth real quick, Logan?
Well, see, the depth is going to be how we will indicate to ourselves as we're walking deeper into the tree as to exactly how far we are in the hierarchy. Because every time we go down a child, we want to mark that as we've increased our depth by 1. So every time that we walk down into the hierarchy, we want our depth to increase. What this allows us to do is when we start to visually display where we're at in the hierarchy, we can use that depth. For example, if we wanted to have an indenting system so that the deeper we are, the more we indent to display children. If we use the depth, we can use that to tell how far we should indent, and therefore give a visual representation of how deep we are in the hierarchy.
Very good. Okay, so now from show tree, let's go ahead and think of some other things we're going to need to do. Well, we're going to need the ability to remove nodes out. So let's go ahead and add just a simple public remove node. Okay, and let's see. And in this particular case, remove node, who are we removing? Well, ourselves. Okay, so now let's go ahead and take a look at another one. How about the ability to, let's see, which one? I don't even think, I know what we'll pick on. How about find? Find's going to be a big one that's going to become really important because we're going to start introducing the command system a little bit later. And in the command system, we're going to want to do things like rename nodes, etc., etc. And this is going to require us to go out to the hierarchy and find these specific nodes. And if we find them, handle the operation that we've asked to, well, do.
Right, it's actually something we haven't delved into too deeply at this point because we've shown how things are connected reference-wise. We haven't really, and we've shown that everything has a name and that name is meant to be an identifier for the node, but we haven't explained how that actually works. What that means is we have a string identifier, but we have actual references pointing to memory. And we need some system by which a string name can be looked up in the hierarchy and return an actual reference, because that's going to be the key in working with this as far as human input goes, because a person is going to type in the name of a node and be expecting to try to find that node, and what he's expecting to grab is a reference to it. So we need to have some way of taking in a string textual name and then looking for a node that matches that name, and that's where the name of the node itself comes into place. And to accomplish this, what we'll do is we'll add a find to nodes so that we can call upon find, feed it the string that we're looking for, and have it, well, A, look at itself and see if it matches, and if it doesn't match, begin to look through all descending nodes and see if there are any matches in any descendant.
Actually, in this particular case, look how I'm setting it up. I'm setting it up as static. So we can just simply say, we don't have to worry about any transform nodes specifically. We can just say transform node dot find and tell it the name and let it worry about going in there and finding that node, period. Now we can get down to specific finds that are based off of
individual nodes.
Yeah, off of individual nodes.
Kind of like if you look back up at show all versus show tree, where show all is meant to grab every node and every transform node in existence.
Yeah.
Whereas
show tree caused me to trip up and stutter real bad a second ago because I was trying to get out it deals with the current instance of the transform node.
Right, whereas show tree, if called for some descendant, is only going to show that remaining branch or that remaining tree. And find will work in a similar manner. The static version is meant to look through all nodes. It's going to go through all of the roots, go through all of the descendants, find everything. What the find for an individual node is going to do is kind of like the branch mentality. Start at the given node that it was called upon, check itself, and then check any descendants.
Right.
So that way it's not necessarily going to find everything in the scene. It's only going to find starting at the point that you called it at.
Exactly. Now, find node is going to get even more interesting than this, and there's going to be another method involved with find node. But we'll talk about that one when we get to it specifically. So right now, let's just keep it broken up into just two different methods. One that is a static find, so that I can say transform node dot find my ball. And then it finds my ball, and it returns, you'll notice we have a return here, returns a reference of node type pointing to my ball. And same thing goes with find node. In this particular case, find node is an instanced method, okay, that will start off with this and begin looking for a particular node and return, if it finds that node, a reference pointing to it. All right, so we'll just leave it as that. When we get to the find area, Logan, I think what we'll do is just make that its own video so we can spend a bit of time talking about exactly what's happening with the code, because it definitely gets tricky. Okay, all right, so let's see, what else have we had? We've got just about everything that we need here. Well, I guess we could go ahead and add some grouping in as well. So let's just come down here, and let's just go ahead and add in a public static. Because remember, the whole idea with grouping was just to be able to say group this node, or you could say group this node and this node. And the idea was that a new transform node is created at the root level, and the node or two nodes that you have specified get parented to it. Okay, so let's go ahead and we'll just create two different methods. Bottom line is they'll just have two different overloads. So first one is going to return, of course, nothing. And it'll be group. And what it'll take in will simply be a transform node. Node 1. Hang on, that looks horrible. So node 1, and it's going to take in transform. And let's go and just visualize the word node there and here. Okay. And a transform node, node 2. So bottom line is the static group will take in transform node, node 1, transform node, node 2. So it takes in two transform nodes. Or we can have a flavor of it that takes in a single transform node. So transform node, this time I'll remember to write out node, node 1. Now there are definitely more elegant ways of setting this up so that you can simply say that we want to do a group, and here is a list of, or a group of, or a collection of transform nodes that we would like to all be grouped. But right now we're keeping it very limited to things that you have seen all the way up to this point. I just wanted to point out there's definitely a cooler way to do this. But we'll just make this very straightforward. You can rather group two transform nodes, or you can group a single transform node. All right? So Logan, looking at this, is there anything else in the requirements for the transform node class that we're missing? I know there are in regards to some shape stuff, like set shape node, etc. But we'll revisit that once we start introducing shapes. So right now we want to just keep this architecture focused only on the transform node. Anything else you can think of?
And with that, no, I think that covers it. That's both I would say, in a sense, most importantly, the fields, so that everything can be connected to everything else properly to make both hierarchical and simple relationships, so that anything relevant can be looked up from any node, and that nodes can be walked through because we have child and parent references. Then, of course, we're hinting at how this will work now by listing the methods that we're planning to use to accomplish this. Because, of course, with the fields we can store the connections, but we need some way for those connections to take place. We also need some way for transform nodes themselves to be created.
Right. So we've got creation, we've got setting the parent, we've got the ability to come in here and show all transform nodes. Once again, it's static. We have the ability to show a tree starting with ourselves and all children below us. We have the ability to remove ourselves. We have the ability to find a node based off of its name anywhere in the hierarchy. We have the ability to find a node starting from ourselves, working our way down the hierarchy. We have the ability to group two different transform nodes together, or to group a single transform node together. And then up here at the top, we are storing all of the relevant information that we showed back over on the other whiteboard, showing what the memory would look like with all of our different classes and instantiations in play. So we've basically covered everything we need to store there. Right. So anything else you want to add, Logan?
Just being nitpicky, knock some of the terminators off some of those methods. We're not trying to be tricky and make abstract methods. We're
okay. Well, no, you guys ignore that.
I was just saying, it's like not hinting at, no, these aren't abstract methods. These are
they're not abstract methods. But anyway, so anything else you want to add to this?
No, I think
that covers all of the functionality that we want to put in.
That's all of the planned functionality for transform nodes.
Right. Okay, so with that, that is going to wrap up this video, and in the next video, we shall begin coding. So that's going to wrap it up. Thanks a lot, guys.